Hi, everyone. How's everyone doing? Okay, so we're going to wait a couple more minutes before we get started. So I'm trying something new here as well. So now I'm providing two options. So for people that want to join the Zoom call, I think that's kind of the preferred method. Is with Zoom, you actually can use your audio. So far in our talks, like no one has attempted to use the audio option, and most people prefer to use the chat option, which is great. You can ask your questions, but know that if you want to if you want to speak as well to ask your questions, that's totally fine as well. But I am providing the second option, which is a YouTube live stream. So for those of you that prefer to connect with the YouTube live stream, I have an additional stream happening at the same time with this one. It will be a little bit delayed, the stream, but that's totally fine. There's not much of a delay, and if you have any questions, you can also ask them there. I just wanted to provide both options for people, just to provide some kind of convenience. Okay, so our speaker should be here in a couple of minutes, and we should get started soon. Okay, perfect. So our speaker is here now, and we should get started. Okay, so today's talk will be about a particular framework called TextAttack, right? This is also an NLP related talk. So if you are really interested in NLP, you're gonna love this talk. So Jack is gonna talk a little bit about this framework that he worked together with some colleagues of his on data augmentation and adversarial training in NLP. So it's really useful for that. For those of you that are interested in any of those topics, you will definitely find this useful. So I just want to say thank you, Jack, for for joining us today and for accepting the invitation to talk here in one of our meetups. This is very helpful. A lot of students join us. Of course, also people from the industry also join us, and it's very yeah, we appreciate it a lot. Your participation. So Jack is just Jack Morris is a researcher at the University of Virginia. Right, he's interested in computer programming and for understanding language, right, and the world around us. He, like I said, is the co-creator of TextAttack and has participated in other research projects related to the robustness of NLP models. So I really like this topic of robustness in NLP models. I think we should be emphasizing a lot on this, and that's why I kind of invited Jack to talk more about this topic as well. And he'll begin the Google AI Residency in October. That's an awesome job on getting in the residency. I know this is very difficult, so congrats on that. Outside of research, Jack likes cycling, reading books, and watching baseball. He will talk a little bit about himself as well as he introduces himself during the talk. So welcome, Jack, and welcome everyone to this talk. And then I will just now hand it over now to him.
Thank you. Yeah, I'm really excited to be here. I was really happy when you messaged me. We just made a bunch of changes to TextAttack. We actually we're submitting a paper about TextAttack to this conference, EMNLP. They have this section that was new last year called like the systems demonstration section, which was perfect for us because it's basically related to big NLP open source projects that are useful for the general public. Oh, let me turn on my video.
Yeah, that'll be okay.
1 second, everybody. But so anyways, we just made a bunch of changes and we just put a new version of the paper online. And so I'm excited about that. Glad to talk to people about it and hopefully show it off. I'll give you all a little background. So I started doing research at this lab at my university, University of Virginia, on the topics related to NLP, specifically deploying NLP in practice and like the robustness of NLP systems. And so that sort of started us to get interested in this idea of adversarial examples and as that might pertain to models that understand language. And then from there, we ended up working on TextAttack, which we started around a year ago. And then that became open source a couple months ago. And so now we're kind of like trying to get feedback from people and hopefully eventually more contributions from the community. And we've added a lot of stuff to it. And now I'm interested to hear from people like you all about what direction you think it should go in, improvements we should make, and generally maybe things we could fix about the framework or API, how it is now, with like not in terms of general additions, but in terms of like improvements to the code quality and things like that. So if you want to reach out, we got like a Slack channel and you can always post issues on GitHub and stuff. And I have a little presentation and demo I was going to do today. So let me just share my screen. I can just start the presentation. Okay. Okay, can you see this slide?
Yeah, we can see it.
Okay, awesome. So this presentation is basically about TextAttack, which is our software, and it's an NLP library written in Python, intended to be used in Python or via the command line, that's based around this idea of an adversarial attack in NLP. So that enables us to do research on adversarial attacks and use them to understand our own models. And it also has two other interesting features, which are about training models, training more robust models, and training better models using data augmentation, and then just data augmentation in itself, which is also sort of an open problem in NLP, whereas it might be a little bit more well-defined in vision. So we'll talk about that. But those are the three basic modules: are adversarial attacks, which are a component of TextAttack, data augmentation, and adversarial training. And if you're not familiar with any or all of those things, that's great, because I'm hopefully going to start from the ground up, and by the end of this presentation, you'll understand what I'm talking about. So first of all, I'm going to explain a few use cases of TextAttack and maybe who it's used for. Some common use cases for TextAttack are to construct these attacks on NLP models based on these components we have, to run the attacks on models that you provide and data sets that might be your proprietary data sets or things that aren't online, but you still want to use the tools for. There's a lot of tools for visualization of attack results and different statistics about attack results related to models. You can create new attacks. You can do data augmentation, which is actually a very similar process to doing an adversarial attack, which I'll talk about later, and uses the same components. or you can do model training and adversarial training. And so TextAttack has some main goals to be like really easy to use. We want to have really high quality code. We want things to be very modular. So for example, if you implemented a new sentence encoder, something that's a model that takes a sentence and compresses it to a fixed length vector, which is a common task in NLP and has a lot of different uses. You should be able to implement that in one place in TextAttack. It should be able to be imported by anyone who installs TextAttack and shouldn't require them to download anything. And then it should be able to be reused throughout the code base. So we have these goals of like writing really good research code, and making it really accessible to users, even if you don't work at Facebook and have like 500 GPUs that you can just use. I want it to run on a laptop, where that's feasible. So that brings us to the next slide, which talks about who TextAttack is for. There's different uses, but I think the modules are useful for everyone. So I was talking about this idea of modularity, whether you implement a sentence encoder or some a different component, which I'll talk about later. You can always import TextAttack and just use that one component, and that should simplify your workflow. Because if any of you have been working on any sort of cutting edge NLP products or really anything related to machine learning, you might know just the environment setup can be really hard, just downloading things, installing them, moving files around, making sure that the versions of packages you've installed are compatible with one another and with your system, and reproducibility is always a problem. So we're trying to write really, really good code that anyone can just download, import TextAttack in one line, and it should set everything up for you. So the ease of use is a very main goal. The main users of TextAttack would probably be researchers who are interested in this idea of adversarial examples in NLP, robustness, which is basically the buzzword for how susceptible a model might be to adversarial examples. TextAttack is also useful for pretty much anyone practicing machine learning as it pertains to NLP, whether you want to try out the attacks on your own models, whether you want to use the adversarial training module to improve your model's robustness. And anyone training an NLP model can use TextAttack. The data augmentation tool is especially useful. I'll talk about that later. I think that's probably been the most popular thing that I've heard from people about on average. But we'll see how that changes going forward. Anyways, there's a lot to like here, and there's many different uses. Even if the idea of an adversarial attack doesn't seem especially relevant to what you're doing, there's probably something else that is. Like I was talking about, that goal of ease of use, I think one thing that TextAttack enables, even though it might not have been our initial goal, is just training models. Even if you're not interested in data augmentation or adversarial training, we have this really easy to use model training code. So you can just install TextAttack and type from the command line. There's a TextAttack command once you install it. So you could say TextAttack train, say the name of the data set you want to train on, the type of model, and then you can specify things like the learning rate and the batch size, the sequence length to use for training, and it just works. It'll train a model. It'll tell you where it's outputted. And so you can actually train state-of-the-art models like fine-tuning BERT on any of the glue tasks or anything like that, just using TextAttack, even if you might not be presently concerned with robustness or anything related to adversarial attacks. But I'm getting a little ahead of myself. I want to start by talking about adversarial examples, just give a little baseline if that's something you've never heard of. And then we can have a discussion about what adversarial examples are in NLP, which is, it's an open problem. It's something that people have had a lot of debate about. There's still ongoing discussion, but the general consensus is that the idea of adversarial examples, though it's very well defined in other spaces, is not in NLP. So, and that's something I'm really interested in. It's sort of a philosophical question, and if you want to have a discussion about it at the end of this talk or ask me questions offline, I'd love to talk about it. Then I'll talk a little bit more about TextAttack for you engineers out there, give some implementation details. And I want to do a little demo in a Colab notebook. I just have a tab open that I can just show you all a quick attack. Then I'll talk briefly about data augmentation, and then I think time will probably be up around then, and I can take questions. So let's talk about adversarial examples. Adversarial examples, oh, can you all see that? That's better. Adversarial examples are changes to inputs that fool the model. That's the most basic definition put out there by some high profile researchers who are responsible for some of the most groundbreaking work in adversarial examples. And they're also known as adversarial perturbations, which some people say is preferable because the word perturbation implies some sort of change from an initial input. And a program that repeatedly generates adversarial examples is known as an adversarial attack. I know that's a little redundant, but that's the terminology. We use it, it's standard. And then when you try to measure a model's susceptibility to these adversarial examples by running an adversarial attack and collect statistics about it, the quantity that you're measuring is generally known as robustness. And so you'll probably hear those thrown around a lot. That's sort of a basic example. You guys might have seen something like this before. This is the original kind of like thesis that spawned a whole host of research and adversarial examples. So if you're solving some task in vision, you have an input and it's trying to be classified within some set of classes. Maybe you have a classifier that's distinguishing pigs from trees, from different dog breeds. I think this might be, I think this is an ImageNet classifier that this example came from. So the shocking realization here is that you have this example that is classified as a pig, probably with some very high confidence. And if you add a tiny bit of noise, so small that you can't even notice it with the human eye, these are probably about the equivalent of one, maybe less than 1 out of 255 in the RGB color space, you end up with an image that's grossly misclassified. And it turns out you can do this with about any image. And if you orient your noise correctly, you can point towards about any class. So you can make this pig look like anything else that the classifier is trained to recognize. And this is really, really compelling and pretty scary if you think about the different very real world use cases that are already out there for CNNs, like self-driving cars, facial recognition. Those models are just as susceptible to adversarial examples as the ones we discuss in papers. So this is like a very pertinent security threat, and it spawned this super hot field of research. Oh yeah, this paper was Intriguing Properties of Neural Networks, 2014 in Goodfellow. I'm not sure if this video is going to work. I was kind of messing with it. This is just a page that was supposed to have, what does it say? A complete list of all adversarial examples papers. I just took a screen recording of this earlier because it disappeared. Because I thought it was funny. Basically, there's thousands and thousands of papers that have been written against this idea of adversarial examples. First, specifically with convolutional neural networks, people proposed attacks, people proposed defenses, and there's some methods that have been proposed to work very well, but there's this inherent trade-off between the accuracy, the ability of the model, and the robustness, its susceptibility to these adversarial examples. So, for example, this attack PGD, projected gradient descent, was proposed a few years ago, and when used as a defense method, they found out they could train models that were like, relative to vanilla convolutional neural networks, very, very robust. But there's a trade-off between robustness and accuracy. So a model that's maybe 95% accurate on the test set is very unrobust. It lacks a lot of robustness. When retrained with this defense technique, might be very robust, but its accuracy would probably drop at least 10%. So this is a very open problem, and none of our current techniques have solved it that well. But as I showed in the video, there's a ton of people that are doing research on adversarial examples. Same within speech, like Alexa speech recognition. That's a very popular area where adversarial examples can be particularly devastating. And it's very natural to ask, what would the analog be in text? Like if you have this picture of a pig, adding a little bit of noise to it, it's being misclassified. This is a pretty easily approachable example of a problem. This is a huge problem if you're deploying CNNs in practice, but it's not immediately clear how or why this would apply to models that deal with language, specifically because this notion of imperceptibility, if you showed someone this pig on the left and the pig on the right, and you ask them which one was correctly classified and which one was incorrectly classified, it's physically impossible to tell the difference. The difference is so slight, and the directionality doesn't indicate which one should be more of a pig or not, that you can say that the difference between these two images is objectively imperceptible to a human observer. But as you can imagine, you couldn't have a string of text when perturbed looks identical to the output string of text that receives a different classification. If there's an imperceptible difference between two text inputs, then they are the same. So some people have proposed different ideas about like what adversarial examples are in NLP if there's no notion of an imperceptible change. And I'm going to talk about two of them. We've implemented a whole slew of these in TextAttack. So the first idea for adversarial examples in NLP are examples that are visually indistinguishable to humans. This is an input to what we would think would be a sentiment classifier that is a text classification model that predicts whether something is positive sentiment or negative. It says, True Grit was the best movie I've seen since I was a small boy. You can imagine this is a positive review. The person liked the movie True Grit. Now we added a few typos here. Movie got changed to moiv, switched 2 letters here, and since was changed to snice. So they switched around 2 letters there, and the prediction changed to negative. This is pretty interesting. And if you are deploying one of these classifiers, or if you're deploying a translation model, for example, they're very abundant. Like they come out very easily, and for pretty much any input you can find something like this, which is really interesting. But I think the field is sort of strayed away from this idea of an adversarial example, and fewer people are researching it because it's actually pretty solvable. Like there's some defense. Oh, didn't finish this bullet point, but there's some defenses that are just effective. So the first one I suggested here was you could just pass inputs into a spell checker. So if this was your system and you said, I don't want to be susceptible to this type of adversarial example, you could just make sure you take the inputs and spell check them before you feed them in. That would avoid this type of error. And the second thing I was going to write was that you could also train some kind of model to actually like correct the original input. So you could build a big data set of a bunch of examples and their perturbations like this, 2 columns, and then train some kind of text generation sequence to sequence model like a recurrent neural network to take the perturbed input and then reconstruct the original input. And then when you feed the examples into the model, first feed them into this kind of like grammar checking model that you trained that would try to make inputs like normalize inputs before feeding them into the model. And there's some people that have tried that using RNNs and other things, and it also works really well. So these attacks are problematic, but they're also solvable. And I would imagine that if you work in industry, people probably have come up with their own techniques like to try and combat these types of adversarial examples. So here's the second one, which I think is more recently common in the research, is that instead of trying to make character level changes that are indistinguishable, maybe if you're reading fast to the human eye, make a sequence that's indistinguishable in meaning to the original input. So if we take the same sentence, True Grit was the best movie I've seen since I was a small boy, originally correctly predicted positive, we can swap out words for their synonyms. So this one says, True Grit was the best movie I've seen since I was a wee lad. You can see that small was swapped for a synonym wee, and boy was swapped for a synonym lad. If English isn't your first language, these are just sort of relatively obscure terms that mean the same thing. So if you ask someone whether the input on the left and the input on the right have the same meaning, it might vary ever so slightly. You know, you could argue that wee lad has a different, I guess the linguistic terminology is pragmatics. It has a different kind of like style than the original input, but the meaning remains the same. And if you train a text classification model, you want your model to be invariant with respect to meaning with its output. So if you predict positive for sentence on the left, you should predict positive for any sentence that has the same meaning as the sentence on the left. So this is a problem these are somewhat easy to find, and it's an unsolved problem. This indicates some deficiency with respect to our current model's understanding of language. And so this is a second definition of adversarial examples in NLP. It's different than the first one that I showed, but I think they're both equally applicable, maybe in different situations. And if you're trying to deploy an NLP model in production, you can probably run into the same type of thing and decide what makes sense to you to defend against. So I'm going to talk a little bit more about how these are crafted, because that's a pretty common research topic. So if you have this input, how do you actually determine what words to change and what words to substitute them for? This is a also kind of like unsolved problem. It's impossible to generate all the paraphrases for a given sentence, or if you were able to do that, you'd have a full understanding of language. So one simple heuristic is take the words, look them up in a thesaurus, and then try all the synonyms. And if one of them changes the prediction, you stop. You found an adversarial example. Another way to do that is to take word embeddings, vectors that represent words. A very common type of word embedding, still sort of the current state of the art, are glove word vectors. They're maybe 3 or 4 years old, which I guess is a little old for NLP, from a group at Stanford. They just trained these word embeddings on a very large corpus that give really good representations of English words. So the idea is, if you have the word embedding for boy, you can look at the nearest neighbors in the embedding space, and you might see child or man or other words that are very similar. But the problem with using these embeddings for word substitution is that, according to the word embeddings, you'll also see a synonym for boy like girl, or another word that might appear in a very similar context but have a totally different meaning. Like if you look at the nearest neighbors of great in the glove vector space, one of its nearest neighbors is probably terrible or awful, because those words are used in very similar contexts, even though they totally negate the meaning of whatever context they appear in. Or sorry, their meanings are totally negated from one another. So there's this third idea. There's a paper from 2016 that proposed this type of word embedding that's called the counterfeited word embedding. And the counterfeited word embedding it's a post-processing step on glove word embeddings. They take the word embeddings, and then they also use a thesaurus, and they do this, they apply this function that's supposed to make words that are synonyms close together in terms of their angular similarity, and words that are antonyms further apart. So that effectively solves at least the very large majority of the cases I said, like how great and terrible are probably close together. Now they should be close to 180 degrees apart, and great and wonderful should be even closer together because they're synonyms in the thesaurus. So people that have been trying to find these adversarial examples based on word substitution generally use these counterfeited word vectors. We'll come back to that in a minute. So these are one of the main components in TextAttack. These are the transformations, as we call them. So a transformation is something that takes a text input and produces another text input. You can imagine for the counterfeited word embeddings, the transformation would take all of the words, look up their embeddings within some finite distance in the embedding space, and then return all the possible sentences made from substituting words with their neighbors. That's the first of 4 components that are integral to TextAttack. Now, what if we did that? What if we took an input, we substituted words with their neighbors, and then we ended up with some perturbations? These are some examples of things that could happen if you chose that route, and they're probably bad. So the first one is basically what I described before. If you look in the glove vector space, you could replace best with worst because they're very similar. And even though you do this counterfeited post-processing step, embeddings are very noisy, and there's a chance that maybe best and worst were neighbors anyway. Movie for film, I would argue, is a very, very well-preserved semantic substitution. And then here, what if you substituted I was for me were? That probably contains about the same semantics, but that's grammatically incorrect. Saying since me were a small boy is invalid English. So after we do that transformation step, it's useful to have some kind of sanity checks on the adversarial examples that confirm whether or not they're they're valid, like whether we would consider them fooling the model. Because I think within most general use cases, neither of these would be really useful to anyone. This one is just not a sentence that most people would ever produce. And this one actually changed the label from positive to negative. So worst film is correctly classified as negative. So the question becomes like, what can we do to ensure that the transformations that we consider are actually valid adversarial examples? And that brings us to this idea of semantic meaning. So one idea that people propose is embed these sentences into vectors, like I mentioned at the beginning of this presentation. One common way to do that is the universal sentence encoder, which is a model from Google that takes methods or takes sentences and encodes them into fixed length vectors. So back here, we could encode True Grit was the best movie I've ever seen into vector, say X, and then take True Grit was the worst film I've ever seen and code it into vector X add. And the hope is that the universal sentence encoder would tell us that the sentence vectors for these two inputs are pretty far apart, maybe even close to being orthogonal. So if you did that kind of constraint, you could say, okay, the universal sentence encoder must state that these sentences are within 0.1 or some very, very close cosine similarity. And if not, we don't include them. Another idea to get rid of the second one would be just pass it through a grammar checker. We could, download some open source grammar checker like we've done in TextAttack and make sure that these perturbations don't include any grammatical errors, or at least don't introduce them from the original input. So that's something that we see pretty frequently. And in TextAttack, we call these constraints. So every attack has transformations, which propose ways to take the input and change it without preserving meaning. But since that's an NLP hard problem, we apply these constraints as sanity checks to make sure that we preserve grammaticality, preserve semantics, etc. And there's two more components I'm going to talk about. If you have these transformations and constraints, maybe the naive way would be, okay, take all the transformations and search through all of them to find the best one. But you can't. If you think about just the dimensionality of the search space, this input that I showed was very small, I'd say, on the NLP side. Like the average movie review might be 100 words. So if you have 100 possible words to substitute, and you consider 10 words at each position, then you end up with 10 times 10 times 10, which becomes 10 to the 100 possible combinations of word substitutions to consider. And you can see how quickly that grows intractable. So we need to find a way to search this space without considering every possible transformation or every possible combination of transformations, but still find a valid adversarial example. And we also need to come up with some way to tell whether our example fools the model. So in this case, the sentiment classification case, we can say, okay, if the prediction changes, we fooled the model. But there's some more subtle use cases here. For example, if this was a translation model and these were two translations produced for the original input, if these inputs were producing different translations, you'd have to come up with some more nuanced way to indicate whether the model's been fooled. So these are the two final components. One would be the search method, which comes up with some heuristic for pruning that gigantic search space and trying to find promising examples without letting it explode and never finishing the search. And we call this the goal function, which indicates whether the model's been fooled. So one thing would be, has the classification changed? That would be what we call an untargeted goal function. You could say, has the classification changed towards a class that I'm interested in changing it to? That's what's generally called a targeted goal function. And for sequence to sequence models, things get a little messier, but some of them are really interesting. Like you could try and perturb the input to try and minimize the overlap between the original translation and the new translation. So basically change the transformation by as much as possible, maybe in terms of the number of the words outputted or the characters outputted. And you can find some pretty drastic flaws in your models. It's actually really interesting and kind of motivating for me as one of the creators of TextAttack, how easy it is to find these models, even when we have relatively tight constraints. So in TextAttack, an attack is composed of a transformation, a set of constraints, a search method, and a goal function. And you might imagine how these can be used for more things like augmentation and adversarial training, etc. Oh yes, I forgot we had a slide about this. So transformation generates the potential XABs constraints that make sure maybe we don't change the semantics unwittingly or violate grammaticality. There's a goal function that indicates whether or not we've actually fooled the model. And then the search method that navigates this gigantic search space and performs some sort of like combinatorial search and tells us when we find a successful adversarial example. Then, since I said before, we want to make our code very modular and very reusable. These are all abstract classes in TextAttack. One's called search method, one's called goal function, one's called constraint, and one's called transformation. And if you'd like to implement a new one, you subclass that and implement maybe the constructor and one or two methods, depending on, you know, whether you want to add a custom string representation or make things more efficient. You might want to implement more. I think I should probably speed up a little bit. So this is a chart I made of the different components we have. I guess, can I zoom? Will this zoom? Exit full screen. Yeah, well, I can post this somewhere afterwards. Basically, we have a bunch of goal functions, a lot of constraints, a lot of transformations, and several search methods that you can try out. And any combination of these is considered an attack. So the interesting thing here is that if you look at the literature on adversarial attacks in NLP, it's a relatively disorganized niche in NLP and machine learning research. Just people have these ideas of what an adversarial example is that are almost the same, but they change one or two details, or they come up with a new method to search, or they come up with maybe some better constraints, more effective constraints, or they just test on a new model and then they release that as a new attack. So the biggest benefit of TextAttack is that we've consolidated this entire subfield of research into this set of 4 components. And I'll give you all an example. This is a paper from AAAI last year called "Is BERT Really Robust?" And they use those counterfeited word embeddings, like I said before, to show these examples like this one here of when a sentence is changed by a few semantics preserving word substitutions, it can fool BERT. So this was interesting because people love BERT, and I think it was the first like very efficient, somewhat usable implementation of an NLP attack in a while. And I'll show you how it fits into the TextAttack framework. So if you go to page 2, they have algorithm 1, their pseudocode for the text fooler algorithm. And it turns out that they're basically just implementing 2 components that are already in TextAttack and then maybe 2 new components. So if we want to break this down real quick, we can look at their search method, which is what we call greedy with word importance ranking. Instead of looking at every position, you do this simple heuristic where you delete each word in sequence and see which word changes the prediction the most when deleted. And you consider that to be the importance of the word. So if you might imagine in the example before, if I deleted best from best movie I've ever seen, the prediction might drop a lot more than when I just deleted, I don't know, grit or something that's not really important for the actual prediction. So instead of trying all the possible words, you try one word at a time in order of importance, and that's much faster. They use the counterfeited word embedding swap. They use the cosine similarity in the counterfeited embedding space. They use a part of speech checker from the NLTK library. They use the universal sentence encoder to compare the sentence embeddings and make sure that, this should say constraint number 3, make sure that semantics is preserved. And then they use the untargeted classification goal function. So with respect to TextAttack, I think the only new component here would be the universal sentence encoder, which since this paper has come out has become somewhat common for these NLP attack papers. So the interesting thing is that we can create the attack in TextAttack by adding a single component, which is really awesome. So this shows, based on the flowchart I showed before, the embedding word swap is a class, universal sentence encoder is a class, the word embedding distance is a class, part of speech checker. These are all classes that are subclasses of the 4 components that I've shown before. And if you take the attack class in TextAttack, you add all 4 of these components and it'll just run the attack for you. And I haven't mentioned this yet, but we're really deeply integrated with these different Hugging Face libraries for tokenization, for models, which is the Transformers library, and then especially for data sets, the NLP library. So TextAttack provides a ton of data sets and models just out of the box. So if you were to implement an attack like this, you could just run it on 50 different models, get all the results, and compare them with all the other attacks that we've implemented, which I think is very useful for the field. This is just a screenshot of the code. It's probably not worth getting into right now, but those are the components. And in the same way, we've implemented 16 different attacks now. So these are the attack names in TextAttack and the citation. These 4 columns show the 4 components: constraints, transformation, search method, and goal function. And these are the 16 attacks. Where's text foolers here at the bottom, and they're runnable via another module in TextAttack, which is textattack.attack recipes. Now I wanted to do just a quick a quick demo. Can you all confirm that you can still see my screen, this Colab notebook?
Yeah, we can see it.
Okay, cool. So I just started up right before this.
Jack,
Okay.
blowing up the text a little bit bigger so it's
Yeah.
easy to see.
Good idea.
Thank you.
Okay, cool. So like I mentioned before, one of the cool things about TextAttack is we want to make it really easy to use. Okay, yeah, so this is just me asking for help about what the arguments I can provide to this TextAttack attack command. But actually, real quick, I want to step back and show you 2 things. So let's go to TextAttack first. This is our GitHub, qdata/TextAttack. It has a lot of demos and documentation, things like that. But I'm pulling this up because I want to show you that we have pre-trained models that we host in the Hugging Face Model Hub and on our own Amazon bucket. That's what here we call the TextAttack Model Zoo. And so instead of training your own models, if what you're interested in is just trying out attacks, instead of trying to test the robustness of your own models, you can use these pre-trained models. So these are categorized by model and then data set. So these are our models based on our just regular LSTM implementation, word-based CNN, and then a bunch of transformers. So these are models that were trained using Albert, BERT, Distilbert, etc. And the reason we can do that is because we have all the model code neatly implemented, and because of this NLP library. Oh, this is what I want to show you. So Hugging Face makes all these great NLP tools, and one that we really heavily rely on is actually called NLP. I don't know why they named it that. It's just data sets, but there are a ton of data sets. So we implemented like an integration with NLP, and now you can access any of these data sets. So since we have training code, and we kind of like wrapped it all up into our training code, you can train an NLP model on any of these data sets just using TextAttack train and then specifying the name of the data set from the command line. And so we've been trying to add some data sets to their library, news, which is a classification data set that people use pretty frequently in the literature. And then we take models like this that are pretty common in the literature, and then we try and fine tune our own models on it and post online, so that when we compare attacks, we can have like a very fair comparison, because instead of people training their own models on the same data set, we all test them on the same model, which enforces actually a pretty significant, like maybe 20% degree of consistency that didn't exist before. So I'll show you an example of an attack, and then maybe like I'll just show you how to run a training loop real quick. Let's go back to the slide and see the attack recipes. So you can specify any of these via the command line. I guess I'll do text fooler because that's the one I've been talking about. So you can say recipe text fooler and then specify the model to attack. Since I haven't trained a model in this Colab notebook, I'll use one of the pre-trained models. What's a good one? I like using this Rotten Tomatoes data set because the inputs are very short. Let's try this. SST2. It's another classification data set. That's from the glue benchmark. And I'm saying do 10 examples. Yeah, I think that should do it. So just to be clear, I started this Colab notebook literally right before my presentation, like 12:59. I ran the installation. There's this, I specified this dependency because Colab is weird. Colab has its own version of this pyro thing, and sometimes it's very persnickety. So I didn't want to worry about that. But basically, I just did pip install TextAttack, just ran the import to make sure it works. And now I'm running TextAttack attack. So it needs to download the model. I'd imagine it needs to download the embeddings. Yeah, so it's downloading the embeddings now, the word embeddings that are going to be used for the word swap. And then pretty soon it should just get into the attack. I probably could have downloaded everything ahead of time. But yeah, I think that this is a very major pain point for people that are even just trying to do NLP in industry, like not even trying to reproduce people's research, which is a whole nother issue, but people that are just trying to run research level code or code that runs NLP things that are pretty cutting edge can just be an absolute pain. So like a very major goal of ours is to make sure everything downloads for you. So you can see it just configured the environment, downloaded the model that will be attacked. Paragram CF is counterfeited paragram word embeddings. It's just the word embeddings I was talking about. Downloaded the universal sentence encoder. TensorFlow printed a ton of stuff. Now this is the representation of the attack, which is TextFooler. You can see this is the greedy word swap with word importance ranking, untargeted classification goal function, word swap based on counterfeited embeddings, and then it has these constraints. I'll just go through them super quick. The words that are swapped have to be within a certain word embedding distance. Words have to have the same part of speech, but nouns and verbs can be swapped for each other. That's just something they did in the paper. The universal sentence encoder within this certain similarity threshold. No words can be modified twice. Don't modify any stop words. And then another thing from the paper, if you're attacking an entailment model, you don't touch the hypothesis. So now it's working and it's printing lots of things. Let's look at this. So this is a film review. The most hopelessly monotonous film of the year. Noteworthy only for the gimmick of being filmed as a single unbroken 87-minute take. Kind of funny. And they changed hopelessly monotonous for lethally humdrum. And then gimmick for thing. I think that's actually decent. I'd probably have to go to the thesaurus to make sure that, go to the dictionary and make sure those words mean the same thing. But that caused a positive misclassification, which is pretty interesting because this is definitely, this is certainly a negative review. And then it's printing out some more. There's a bunch of different visualization options, like you can print to CSV, you can print to this weights and biases online visualization thing, send people a link, but I honestly, most of the time, just print to a console. So I'm going to rerun this just to emphasize that you don't have to download that stuff every time. It downloads and it saves to this little cache folder. So even though this takes a little while to start up and load everything onto the GPU, because I think I'm running on a GPU, yes, it's much faster because everything is already downloaded. So 15 seconds to load. Yeah, now it's printing out the same stuff. Yeah, and it didn't change. That's awesome. That's something we've struggled with, is like consistency based on all these different random seeds that are set by different packages, but I think we got it figured out now. So I'm going to go back to the presentation and then I'll show you real quick what training looks like, and then I'll take some questions. So that was the attack demo. So we have this model training code that we've implemented that I've alluded to a couple times. It's just TextAttack train, like I ran TextAttack attack. You can also do all this stuff via the Python API, but I've found that for most people's use cases, they pretty much want to stick to the command line. Unless you're explicitly working on some of those components for research, you're probably going to want these command line tools. So we have a model training loop with a bunch of options that's written in PyTorch. We have an LSTM and Word CNN that are just kind of like standard models that people can compare. We've integrated with Hugging Face, so we have all the different transformers, you know, Bert, Albert, etc. Recently, we're adding this sklearn training loop, so you can train even more, I guess, primitive models, bag words, other things, and you can compare them, because even though they might be less accurate, they might be more robust, which is interesting to me. All the data sets I showed from NLP. And then the coolest thing is that you can just specify, like you would specify a data augmentation technique via the command line. So you can just say, augment my data set with this transformation and constraints. And it'll just do it. It will just increase the size of your data set with the number of samples you specify and just run training all from the command line. The same thing with adversarial training. You can specify an attack when running TextAttack train, like the TextFooler attack I ran before. And at the end of every training loop, it'll run the attack, append the adversarial examples to the training set, and keep running. So that's sort of the most basic way to do like train more robust models using an attack. This is a demo of the data augmentation module, which uses a transformation and constraints to augment a data set. And this is what I mentioned before as probably being the most common standard use case for TextAttack. And this is using the Python API. So from textattack.augmentation, import the embedding augmenter, which is just something I made that's kind of just like reasonable decisions about how close words have to be in the embedding space to be considered synonyms. Then just call augmenter.augment on a string, and you'll end up with all these different augmented versions of the input. So what I cannot create, I do not understand, becomes all these similar things like what I cannot create, I do not fathom. This is with a 1-word substitution as the default, but you can also substitute like 4, 10 words, or you can specify a percentage, like substitute 50% of the words if you want. And that actually has been helping people get better results, which is awesome. This is an example of training the Rotten Tomatoes data set that I showed before, which increased by about 1%. And this is very dependent on the training set size. If you have a really big corpus, as far as I'm aware, it probably won't help much. But if you have a really small one, even smaller than this, like a few hundred samples, data augmentation will absolutely help you, which is cool. Then I don't know if I have time to talk about this, but I really hope that TextAttack helps people work on data augmentation and NLP. Because in computer vision, if you're training a state-of-the-art ImageNet model, you're going to have to do a pretty serious amount of data augmentation. And so many people have tried it that there are some pretty standard recipes for, you know, transforming images, skewing them, things like that people do for data augmentation. But people haven't really tried this much in NLP. I think partially because of lack of tooling, and there's just not a lot of easy to use tools for doing it, and partially because it's not that well defined. Should you use type 1 or type 2 adversarial examples from what I showed earlier? But hopefully people will start to research this more, and we can get consistent improvements in our NLP models as people come up with better ways of doing data augmentation. So in the long term, I really hope TextAttack is good for that. And then that's my slide about questions, but I'm going to show the training function first. I'll just use, I had a sample command I pasted in here. Yeah, this works. This is weird. Don't know where that came from. Okay, so I have this command copied. We can look at it real quick. TextAttack train. So this is the pip install TextAttack, gives you this command. Train, not attack. Specified the model. So this is just the BERT base from Hugging Face. Basically, you can specify any model via a string that's available from Hugging Face, like this stillbert, and they have all sorts of transformers. The data set is the Rotten Tomatoes movie review data set that I like because it's short. I'm actually going to change max length to 64 because we don't really care. Epochs 3, train for 3 epochs, set the learning rate to 1 e-5, which is pretty typical for just like fine tuning a transformer. Oh, and we need an exclamation point because that's how you run bash in Colab. So again, you can do this via the Python API. We have some hooks and functions and stuff that you can integrate into your training code or whatever, or you can just do this. And if we wanted to, we could have specified a data augmentation too, but for the purposes of the demo, it takes a little bit of time to augment the full data set and add it. So I probably could have done that beforehand, but didn't think of it. So this is not using data augmentation or adversarial training. This is just training a model. So batch size 128, that was the default. This is the size of the MR training set, which is loaded via NLP, max sequence length 64, which I specified here. Yep, learning rate, num epochs. Wow, this is fast. The Colab GPUs are really good, actually. They're better than the ones we have in my academic lab. It's funny, but you can only use one at a time. And if you go away from your laptop for 30 minutes, they'll probably time out your runtime for whatever reason. But yeah, this is great. So also I specified a pretty small max sequence length, like the default for BERT is 512. But since this data set is relatively short on average, it was fine. I can get a pretty good accuracy. Well, this is actually doing super well for how short they're being truncated to. After 2 epochs, my model is up to 83%. And I'm just going to wait for it to finish the last epoch. And if I wanted to, once I train this model, I could do TextAttack, attack, -- model, and then this path to the trained model, and I would attack it. But I think I'm going to stop and go to questions now. Yeah, so that's a demo of running training real quick. That was super easy. We didn't have to download anything. It set everything up for us and trained a model. Standard, probably best you can do on this data set is closer to 87%, I think. It's pretty noisy and small, but we didn't do any augmentation, and we truncated all the sequences to 64 tokens, which is shorter than they are. So it makes sense that some information is lost and we can't achieve state-of-the-art generalization. Okay, cool. I think that's the end of my demo, and I'm going to go to this last slide. Didn't this show up without the transparency? That's weird. But the screenshot, okay, actually this is messed up. I'll just keep it like this. This is a screenshot of our paper, which is on archive. It's called TextAttack, a framework for adversarial attacks, data augmentation, and adversarial training in NLP. This is a link to our GitHub, or if you want to just download it and take your chances using the command line tool and -- help, I encourage you to do so. I think our commenting is pretty thorough, and you could probably do some damage just by pip install. Yeah, and then that's the end of my presentation. So I'm happy to hear questions and talk to this with you all.
Thanks very much. Thanks very much for that talk, Jack. That was really, really interesting to see the demo and also kind of introduction as well. I think for most of us that are really interested in the space, I think you really did a great job explaining some concepts and clarifying some things. And as you said, right, it's something that it's just in the beginning phases. So there's a lot of potential to contribute, and tools like this actually give us that opportunity to play around with this. So thank you very much for the presentation. That was really excellent. I have a couple of questions for you, if you don't mind. So yeah. I've collected a couple of them, and the first one that I've collected here is really, really interesting, and I want to maybe maybe about this checklist stuff, maybe you don't, but let's see. So the question is, what's your opinion on checklist, and how does TextAttack fit into its methodology? Are you aware of checklist?
Yeah. That's a great question. So for those of you that don't know, one of the biggest conferences for people working in NLP is called ACL, and it happened recently. And the best paper award they gave out among probably a few hundred papers was checklist paper that talked about the idea, like applying the idea of unit testing in software to NLP models, right? And their results were really interesting. They overlap pretty seriously, I think, with some of what TextAttack does, and then they added some other cool ideas. The first thing they did was really basic. They just did unit testing. So if you're writing a classification model, you can just sit there and write down, probably a few hundred examples. This movie was nice, I did not hate this movie. I liked it. You maybe come up with some trickier ones. And it turned out that their models failed on like a very surprising amount of those. So their argument is that people just sort of train on the data set and they do no sanity checking whether models really work in out of distribution in the wild. And then they had two other things that I thought were really interesting. The first, I think, was they called it like invariance testing. It's basically what I showed in using TextAttack, substituting words with synonyms from some thesaurus and making sure their prediction didn't change. And then the third one was called directionality invariance. And I think that was, I thought, the coolest. And we haven't implemented that in TextAttack, but I really want to. So the idea was if you have a prediction that's like, say you have an input that says, I hated this movie. And then you added a sentence on the end that said, I love this movie. The idea is that the prediction should change in a predictable way. So if you predicted 99% negative, it at least shouldn't go up to 99.9. Your prediction should at least shift in the positive direction. And so they found that by appending like positive or negative inputs, they should change the prediction in a predictable way, but they didn't. Or a lot of the time they didn't. And I think those are the three components of checklists. So the second one is basically what TextAttack does. And I'm hoping to actually add it, the checklist implementation, just as one of the recipes in TextAttack. And then the third one, the directionality invariance, is such a great idea. And I think we're benefited by the fact that our code is so modular. We could probably implement that without too much trouble. So hopefully down the line, we'll be able to support those two types of tests and maybe like provide more like a practical suite for people who actually want to try these, on their models, and make sure they work in production.
Cool. A follow up to that, right? And talking about support, and maybe in the future you're gonna incorporate all of these ideas. How about languages other than English, right? So like low resource languages. How about this one?
Yeah, that's an awesome question. So that's another thing. I guess I'm just very fortunate that like myself and the people that I worked with were dedicated to trying to make everything sort of abstract, which was really annoying at the beginning. But now I think the biggest benefit down the line is that we can support languages besides English. So if you look at the 4 components where's the slide that talks about those? The 4 components, the transformation is linguistic based, word substitution or something like that. The constraints take an input and determine whether it's valid, which also uses linguistic information. But the goal function of, changing a prediction from maybe positive to negative, or the search method that just says, do this greedy thing with word importance ranking, those have nothing to do with the language at all. Those are agnostic of any language. So hopefully soon we'll have community contributors of things like a Spanish thesaurus or a Chinese sentence encoder, and then we can run attacks on models that are not English based at all.
Okay. Do you think like in terms of like contribution or people that are interested in contributing, to different languages, could there be some kind of like guidance or anything like that from the team to be able to do this more easily, since it's already very modular, like you said?
Yeah, right. And that's kind of a downside of modularity, is that it really increases the learning curve, just having everything in all these different files and knowing what commands to run and things like that. So yes, absolutely. That's something that I'm really interested in. There's a GitHub issue. If anybody wants to look at that, that's related to adding attacks in Thai and Chinese. And we're just looking for contributors. And I think the main thing I'm interested in, like adding, and hopefully the community can help with, is attacks in other languages. So if you're interested in that, please join the Slack, comment on the GitHub. I'd love to help you out. Have a lot of free time right now.
Yeah, cool. So really, really interesting questions here. I don't know if I'll be able to ask you all, but let's see. So there's another question about, after you have done, say you have taken a model, right, and it's prone to adversarial attacks. So what do you think is the next step, right, on that?
So I guess I could classify these defense techniques into two types. One thing you could do would be add a pre-processing layer to inputs that you're going to feed into your model. I touched on this a little bit before. So like if you're worried about your model being sort of susceptible to like these changes in grammar or character level changes, you could just add a grammar checker, and that would probably give you a pretty significant like boost in robustness. But if you are really interested in combating like a specific type of attack, you're going to have to retrain the model, at least as far as I'm aware. And so one way to do that is by using adversarial training like you do in TextAttack, where on each step of the training, you run an attack and then you increase the size of the training data set. And that turns out to help pretty well in increasing models' robustness.
Okay, cool. Another interesting question here. Can the summarized, abbreviated, or Twitter-like text of the original be considered adversarial? Another one here regarding that, can the change of voice like to passive, could that be considered adversarial? So this is more talking about different types of adversarial examples.
Yeah.
Yeah.
That's interesting. I think yes. Well, it depends on your use case, right? Like, if your goal is to classify news headlines based on their topic, and then you summarize your news headline in a single word, and it's misclassified, you might not consider that very useful. But I think in the general case, both passive voice and summary are really good ideas for trying to test the robustness of NLP models. Like, and you could implement either of those as a transformation that takes an input and tries to transform it into passive voice, or takes an input and summarizes it. And for most tasks, you could expect that not to change the output, like the predicted output. And so if it did, that would be interesting. And also, I bet it would work. I bet you would find a decent number of adversarial examples. One more point that reminds me of something that I'm also hopeful that the community will contribute is a model for paraphrase, like a sequence to sequence paraphrase model. That's sort of like even less of a change to the input text. And the goal would be that you could apply a transformation that uses paraphrase, and then just paraphrase all the different sentences until you found some arrangement that fooled the model. That would be really interesting.
Yeah, cool. And in terms of like the use cases, someone is asking about use cases here, but do you have any idea, people that are building on top of the TextAttack framework already, or even writing papers around this framework? Any of those examples available online, or are you considering to put them or include them at some time, in the GitHub repo or something like that?
Yeah, definitely. I mean, we haven't had it as public for very long, so I'm hopefully this fall we'll start to see more projects people are working on. We can compile a list or something like that. I definitely could send you all some things right now. I know one thing that my group is working on is so where's this table? So if you look at all these attack recipes, generally it's hard to get an idea of which individual component is responsible for any change, like empirically. So these attacks, if you run one of these attacks against a model, you get this number, which you could call like attack success rate, or sometimes people call it after attack accuracy. And then someone would write a new paper and they would say, okay, instead of using a source, we use counterfeited embeddings, but we also used a different sentence encoder, or we also used a new search method. And it's impossible to disentangle which of those two changes actually is like driving an increase in attack success rate. Does that make sense? So like whether the new search method was useful or the new transformation, for example. And so what we did, like sort of our first paper based on TextAttack, was just a bunch of ablation studies, pretty much like comparing different search methods without changing anything, comparing different transformations without changing anything. And those results were pretty interesting, and I think kind of necessary to move forward. The next thing I've been hearing from some people about in the Slack is explainability, and trying to use TextAttack to explain the predictions of models. Hopefully some interesting things will come out about that in the fall as well.
Okay. Okay. So another question here about data sets. So can you use your own data sets instead of using the NLP data sets from Hugging Face using the command line tool?
Yeah, you can use your own data sets. That's something I've done a decent amount because they have a lot, but they don't have every data set, and if you compile your own, it won't be on there. So there's a couple different ways to do it, but the main way to do it is to just load your data set via CSV, or you can write a file called dataset.py and then specify dataset from file and then dataset.py, and you can load your dataset using whatever format you need, and it'll just load it in and run the attack. Same with the model training.
Okay. So another question, I don't know if you have an answer for this, but it says there are so many data sets in NLP. How do you train on these huge data sets? Did you use any special framework? What was it trained distributedly or anything that you can talk of?
Yeah, a really good question. So, well, first of all, a few of them, there's a few tasks that require some pretty specific data processing. So, like the main example that comes to mind is squad, and you have to do all these different things to get the question answers in the right order and get the spans to match. And so we just flat out don't support training on squad because that would just be like sort of a serious
Right.
undertaking, and I don't think anyone really would want to do that at the moment. But in general, no. I mean, some of them are really big. Like even just some of the data sets. Here, I'll show you all. I like to go on the Glue Benchmark website to see information and stuff. These are the tasks I use probably most frequently. And some of these data sets are really, really big. There's a table in here that I'm going to show here. Actually, maybe not super big, but 391,000 examples is pretty large as NLP data sets go. And another one is the Yelp polarity data set, which has maybe 600,000. Oh yeah, 364. So the Yelp one's a little bigger, but they actually work fine. We can try, see how long it takes, but I think generally training on one GPU in Colab might take overnight, but otherwise it's been fine. Our university lab has 4 GPUs set up that we can use to like distribute. So using PyTorch, there's this data parallel class, and that's worked fine for us.
Okay. See. Okay, so I think the most important question of the moment at the moment right now is GPT-3. Any support for that coming soon?
Oh, it's funny you ask. I'm pretty bitter about that because I haven't gotten my access code yet. But yeah. And GPT-3 is kind of like a Swiss Army knife of NLP tools. It's we could use it. For example, I could probably use it for that paraphrase thing, trying to get it to paraphrase inputs or summarize them as like a transformation. You could use it as a constraint, like, do you think this is a valid adversarial example? Like literally ask that. Or you could actually test the robustness of GPT-3 itself by trying to do these like very slight synonym substitutions and comparing the outputs. The idea being like it should probably respond to very similar things to very similar prompts, and if it doesn't, that might be an issue. So I'm really excited about that. Hopefully I get access soon. If anyone is listening to this and has the power, please please get in contact.
We have a few people in our Slack channel with access to it. I've been meaning to ask them because I didn't get access to. I'm still waiting.
Hopefully soon.
All right. I think those will be it for the questions. Jack, thank you very much. This is really wonderful. We learned a lot here today. Thanks for taking the time with us today and teaching us a little bit about your tool. We're gonna, also spend some time there and trying to help out also with your community and join your channel as well and just provide more feedback. I'm really interested in this tool myself, and I'll definitely take a deeper look after this and provide you some feedback also. Thank you very much.
Awesome. Yeah. In terms of contributions, I'm also really interested in just sort of comments, especially on just how we can improve and how we can make the documentation better, stuff like that. So please, get in contact.
Okay, Cool. Thank you
so much.
All right,
Thanks
bye-bye.
for the time. Thanks
Have
for
a good
watching.
day. Bye.
Bye.